Imagine the universe in its infancy. Most scientists think space and time originated with the Big Bang from that hot and dense start. The cosmos expanded and cooled, but it took a while for stars and galaxies to start dotting the sky. It was not until about 380,000 years after the Big Bang that atoms could hold together and fill the universe with mostly hydrogen gas. When the cosmos was a few 100 million years old, this gas coalesced into the earliest stars, which formed in clusters that clumped together into galaxies. The oldest of these galaxies, thanks to the James Webb Space Telescope, appeared 350 million years after the universe was born. To their surprise, scientists have found that another class of astronomical objects began to appear at this point too: quasars. Quasars are incredibly bright objects powered by gas falling into supermassive black holes, visible across vast distances. Some of the most ancient quasars visible at immense distances appear to be fueled by black holes containing about 1 million times the mass of the Sun. However, conventional theories suggest such massive black holes couldn't form in less than 1 billion years, challenging existing theories like never before. Many astronomers believe these first quasars are powered by seed black holes, remnants of the first stars. However, these remnants should only contain a few hundred solar masses, making it hard to explain how they grew into the massive black holes fueling the early quasars. Adding to the mystery, the James Webb Space Telescope has now discovered a supermassive black hole 40 million times as massive as the Sun, powering a quasar that existed only a few million years after the Big Bang. How did we find such a surprisingly massive black hole in the early universe, and how is it so different from anything ever observed? This is your space. When the James Webb Space Telescope began sending its data, scientists around the world held their breath in excitement because they knew that the observations would challenge the long-held beliefs we held about the cosmos. The Webb observations are divided into different programs, and I have discussed it in length in one of my videos. For those interested, the link is in the description below. During one such observation, scientists were scanning the data that arrived for the Uncover program. 3 very compact yet red-blooming objects prominently stood out and caught their eyes. The powerful Webb telescope used a galaxy cluster called A2744 as a foreground lensing body to amplify light from background galaxies, which are otherwise too distant to see. This revealed the extremely red quasar they zeroed in on, originally in the form of 3 red dots. In other words, it's just one that we see as 3 due to gravitational lensing. Upon more analysis, the object revealed itself as a quasar, seen as it was around 700 million years after the Big Bang. The cloak of thick gas and dust shrouding the black hole indicates its high redshift. But what really caught the astronomy team's attention is the black hole's mass. At around 40 million times the mass of the Sun, it is unexpectedly massive in comparison to the galaxy in which it resides. The black hole is surprisingly different from the ones found during that epoch. Analysis of the object's colors indicated that it was not a typical star-forming galaxy, further supporting the hypothesis that the red, indeed, is a supermassive black hole. Together with its compact size, it became evident this was likely a supermassive black hole, although it was still different from other quasars found at those early times, said the lead scientist of the Uncover program. The finding deepens the puzzle of how supermassive black holes, which can reach millions or even billions of times the mass of the Sun, expanded to such enormous sizes in the early universe. The JWSt has now spotted numerous little red dots that are challenging our cosmology like never before. The JWSt pearls, which stands for Prime Extragalactic Areas for Reionization and Lensing Science, is aimed at understanding the epoch of galaxy assembly and first light. Scientists on board this program were making observations when they found a galaxy they weren't looking for. And what's strange is that there is no way this galaxy should exist, and yet here we are. The James Webb Space Telescope continues to extract cosmic puzzles from the depths of spacetime. The story goes like this. As part of its objective, the JWSt Pearls observation program was scanning a galaxy cluster called CLG 1212 when it suddenly stumbled upon a dwarf galaxy. They named it Pearls DG, marked in cyan, and the green squares show the area covered by the near-infrared imagery. Also, two of the closest massive galaxies in projection are identified by red circles. It is about 98 million light-years away and has no neighbors whatsoever. What also caught scientists' attention is that the galaxy is not creating stars at all, and that is very unusual for an isolated dwarf galaxy. If anything, it should be turning out a lot of stars. But the galaxy is unusual for another reason. While observing it, the James Webb Telescope was able to find individual red giant stars residing in it. This makes Pearl's DG one of the most distant galaxies in which we can see individual stars, and being able to see individual red giant stars makes studying the dwarf galaxy much easier. From the data gathered by discerning these stars, scientists found that Pearl's DG's stellar population is older, and it hasn't formed a star in at least 1 billion years. A galaxy that stops forming stars is called a quiescent galaxy, where the gas that fuels star formation runs dry. Normally, it is caused by interaction with another neighboring galaxy, where the interaction strips gas from the galaxy to halt star formation. But Pearl's DG has no close neighbors. It's as lonely as a galaxy could get. What's more, this type of isolated quiescent dwarf galaxy has not really been seen before. They are not really expected to exist given our current understanding of galaxy evolution. So, the fact that we see this object tells us that we need to improve our theories for galaxy formation. The James Webb Space Telescope is really challenging our understanding of galaxies with every observation it makes. Astronomers have long assumed that galaxies in the early universe would look like orbs or disks, very similar to that of the modern universe. However, new images from Webb reveal that not only were baby galaxies not orb-like, they are weirder than anything scientists expected. Yes, the newborn galaxies of the early universe look like bananas, and mind you, this conclusion comes after a group of astronomers re-examined images of 4,000 newborn galaxies observed by Webb at the dawn of time. Should the findings prove accurate, astronomers suggest that it might fundamentally reshape their comprehension of the processes governing the emergence and expansion of galaxies. Additionally, it has the potential to provide valuable clues about the enigmatic properties of dark matter, an elusive and invisible substance believed to constitute a significant portion of the universe. What is interesting here is that a lot of astronomers won't have it, even though the result from this study builds on hints from earlier observations from the Hubble telescope, which, by the way, had also suggested that the earliest galaxies were shaped like pickles. One of the scientists, Dr. Alan Dressler of the Carnegie Observatories, who played a foundational role in developing the James Webb Space Telescope, is skeptical about this result. Although he was not part of this observation, he said, I retain some skepticism about this result given how hard it is to make such a measurement, especially for galaxies that are far away, small, and not very bright. The team, however, investigated the three-dimensional shapes of galaxies by statistically analyzing their two-dimensional projections on the sky. If these initial galaxies took the form of spheres or disks with random orientations in space, astronomers would expect them to occasionally exhibit their complete faces, presenting as round and circular when observed by telescopes. However, the observations don't align with this expectation. Instead, astronomers are encountering a prevalence of shapes resembling cigars and bananas. They consistently look very linear, said Dr. Pierre, the lead author of the study, with some galaxies showing multiple bright clumps arranged like pearls on a necklace. Such oblong galaxies are rare today, but they make up as much as 80% of the galaxies in the Cosmic Evolution Early Release Science sample, which reaches back to about 500 million years after the Big Bang. Their masses are such that they would be the progenitors of galaxies like the Milky Way, implying that our own galaxy may have gone through a similar cigar or surfboard morphological phase in the past. In the modern universe, galaxies seem to come in two basic forms, featureless roundish clouds called ellipticals and flat, spidery disks like our Milky Way home. Evidently, the earliest newborns didn't start out like that. Back in 1926, Edwin Hubble devised a classification scheme known as the Hubble sequence that segregated galaxies into three categories, ellipticals, lenticulars, and spirals, based on their appearance. Cut to the recent present, and in 2010, a team of European astronomers using data from the Hubble Space Telescope observations created a census of galaxy types and shapes from a time before Earth and the Sun existed up to the present. The team sampled 116 local galaxies and 148 distant galaxies. The results showed that the Hubble sequence 6 billion years ago was very different from the one that astronomers see today. 6 billion years ago, there were many more peculiar galaxies than now, which was very surprising and also meant that in the last 6 billion years, these peculiar galaxies must have become normal spirals, giving us a more dramatic picture of the recent universe. The astronomers think that these peculiar galaxies became spirals through collisions and mergers. Although it was commonly believed that galaxy mergers decreased significantly 8 billion years ago, the new result implied that mergers were still occurring frequently after that time, up to as recently as 4 billion years ago. This study also reiterated that spiral galaxies are indeed young galaxies that have not been around for a very long term compared to other types of galaxies. Now cut to the present, and we have the James Webb Space Telescope that is taking our cosmology for a spin, and its latest finding is another blow to our understanding of the universe. The standard model of cosmology suggests that galaxies evolved over time, forming from vast clouds of primordial hydrogen and helium and likely having a fairly amorphous structure at the beginning. Given the density of the early universe, galactic collisions and mergers were common, which gave galaxies their rotations and caused them to form disks and spirals. All of this takes time, so we would expect spiral galaxies to be fairly common in the local universe, but rare in the early universe. Now, a team of scientists has used data from the Cosmic Evolution Early Release Science Survey, which was gathered by the James Webb Space Telescope. They identified 873 galaxies greater than 10 billion solar masses with redshifts between 0.5 and 4. Galaxies at this redshift are between 5 billion and 12 billion years old, spanning the range of early galaxies to modern ones. Of these galaxies, 216 were classified as spirals. The researchers were careful to note that some may be merging galaxies that were misclassified, but even then, 108 of the galaxies were unanimously classified as spirals by evaluators. When the team arranged them by redshift, they found that while the fraction of spirals decreased as you went further into the past, the fraction of spirals at redshifts above z=3 was much higher than expected. A redshift of z=3 is around 11.5 billion years. When the team calibrated observations, they found about a fifth of galaxies at z=3 are spiral galaxies. These very early galaxies would have had to become spirals less than 2 billion years after the Big Bang, meaning that there would have been little time for mergers and collisions to be the cause. In other words, many galaxies evolved into disk-shaped spirals quite early in the universe. So, while collisions and mergers do play a role in the formation of spiral galaxies, there are likely other factors that come into play, but as of now, we have no idea what they are. May this year reveal a lot of answers. Go Webb to infinity and beyond.